Okay, so again, for the section 3.1, part of our work is going to be just being given some functions and having to find the derivative, which again is no different than what we've been doing with the limit definition, because that was the derivative that we were finding. We just didn't have that name to it. Okay. So what we're going to look at next is I got a couple of example problems that we're going to look at, some typical things that we're going to be doing in the homework. If you look at the information that I have here for this actually comes from number 1 on page 101. It tells us that the function has got a value of 3 at x equals 2, and the derivative at 2 is equal to 5. And our issue here is find the equation of the tangent line. Okay. Well, ultimately, if we're going to find the equation of any tangent line, no matter what information we're given, or any line at all for that matter, okay, if we write down our point-slope form, okay, we already know a point that it goes through, of course, which is 2, 3, and so if we put those into the proper locations, and then the only thing we need to recognize now is that the derivative, okay, is the slope of the tangent line at that point. So if they give us those 2 pieces of information, then how difficult a problem is that? Not really, we just got to fill in the blanks. So the normal line, of course, is the same thing, but with a negative 1/5, the opposite reciprocal. Okay. And that's it. Okay, so that's one typical problem I might be asked to do, is deal with writing an equation for a tangent line. Okay, and we may be given the derivative, or we may have to find it as well. Okay, now I want to look at there's an alternative definition for the derivative that looks like this: f of x minus f of a equals x minus a. Okay, and ultimately, what this definition gives us the derivative because of the fact that we're taking 2 points, a and x, on the curve somewhere, and we're subtracting the y values, okay, and we're subtracting the x values. So really, isn't this just a slope also? Okay. And notice the limit part here is it says x approaches a. Because in terms of x values, what do we want the 2 points in question to do? We want them to get infinitely close to each other. True? So that, in fact, they are each other when we take the limit as x approaches a. Okay. So we're going to use that alternative definition, okay, to find the derivative of a particular function, and we're going to do it with the function in number 3, which is 1 over x. Okay, and I have the answer here. We'll see how we get it in just a minute. But bottom line is, if we set it up properly, if we do the function at x, that's 1 over x. The function at a, it's 1 over a. Okay, and at this point, this is a similar algebra to what we did earlier when we have a complex fraction. Okay. We can multiply by the common denominator on both top and bottom, okay, which in turn wipes out the x for this one, wipes out the a for this one, so we'd have a minus x. Okay. And then in the bottom we have ax times x minus a, and like I did before, I didn't notice I didn't cross those, or I didn't expand that, I didn't multiply those into each other. Okay. And what you want to recognize here in this case, though, is that you have a minus x and you have x minus a. Okay, if they were both x minus a, then we could just cross them out and have just ones. Okay, but we don't. They're opposites of each other. Notice that if I did, 5 minus 4 and 4 minus 5, wouldn't that be the same number, but just different sign? Okay, so in general, if I have a minus x and x minus a, I can still cross those out, but instead of having 1 and 1, I'm going to have 1 and negative 1. One of the two needs to be negative. Okay, so bottom line is, when we get done with that, we get negative 1 over ax. Okay, and keep in mind that we're doing the limit as x approaches a. So if we plug an a in there, we're going to have negative 1 over a what? Negative 1 over a squared. Okay. Now, in this particular case, I would suggest that this is easier to apply than using the first definition that we learned. Because remember, the first definition, we would have had to do a plus h here in a. So the common denominator would have been a little more complicated. We'd had a plus h times a. Okay. Would the work have been much different? Not really. But ultimately, we would have gotten to the same result, but we would have had to deal with that h variable as well. Okay, if you do it with the alternative definition, okay, the algebra is a little bit easier. Okay. Would I use this for every single time I do it? Not necessarily. Okay. Either one is fine, but it is available for you to use. If they tell you you have to use it, like they did in one problem, then you do. Okay. Garrett? That's right, because I'm taking the limit as x approaches a. So I'm putting a in for my x. Okay, and again, just like when we found it before with our limit definition, with our a plus h and a, we find the answer in terms of a, but what is a? A is really just a what? It's an x value, it's some x value. So when I write the final answer here with my derivative notation, I'm just going to say f prime of x equals negative 1 over x squared. Because again, that a is an x value. All right. Questions so far? All right, I want to look at number 5. Says that we need to find dy dx. Again, in 4, 5, and 6, they're just using the different notations that I just talked about earlier. Okay, if we have to find the dy dx of y equals 7x, okay, I could use either one of those definitions. I could use the limit definition, or I could use the alternative limit definition. Okay, but one question that we want to start to answer here is, do we really need to do that to get the answer to this? And if not, why not? What would be the derivative of this without having to do any work? Yeah, because what kind of function is this? It's linear, so what's its slope at every point? Yeah, 7. Okay. And so think about, again, relationship-wise, if I were to draw a graph of y equals 7x, it would be linear, okay? And its slope would be constant. Does that make sense? What we know about the geometry here? Okay, the slope of our line doesn't ever change, does it? No matter where we are, the slope is constant. Okay. Okay. Now I do also want to look at number 19. If you turn the page to page 103. In some cases, we're going to be asked to estimate the derivative, okay, from a table of values, because if we don't have an actual function to work with, then we're not going to be able to use the limit definition and do the algebra that's going to take to find the derivative. So in some cases, like I said, in this one with a table of data, we have a distance in feet and we have a time in seconds, and the directions here are is to sketch a graph of the derivative and then answer the following questions. Okay, so what we're going to do that is going to be the following. Okay, I have on my other side here, I'm making a table here with my same independent variable t. Okay, but my dependent variable here is going to be the derivative. Okay, and so first question is, how did I get 0.5? Okay, what we're going to do in this method, it says use the example 5 method. This is what they did in example 5 too. Okay, my first two x coordinates are 0 and 1, so I'm going to use the middle of those two. Okay, so I'm going to use 0.5 as my first t value, if you will, to graph this derivative they asked us to do. Okay, and then what I'm going to do to get d prime is I'm going to calculate the slope between these 2 points. Okay, and so you'll notice I did 3.3 minus 0 divided by 1 minus 0 and got what? 3.3. Okay. All right. Now, ultimately, that right there is just a point. Okay, that's going to be on the derivative curve, if you will. Okay, because again, they asked us to draw a graph of the derivative. Okay. Now, my next point is going to be 1.5 because that's what. It's halfway between 1 and 2. The next 2 points. So I'm just going to go through and do it with the next 2 points, and I got 10 this time because I did the second data point, third data point, if you will. 13.3 minus 3 is 10. 2 minus 1 is 1, so 10 over 1 is 10. Okay, and so we can go through this process, 2.5, and then do 29.9 minus 13.3 divided by 1. We get another point, 3.5, and then 53.2 minus 29.9. Okay, and what I'm developing here again is an XY chart, okay, for the derivative. Okay, and once I have this XY chart, they've asked me to draw a graph, then what am I going to do with these points? Okay, can I just plot them? If I just plot them and then draw, a smooth curve through them, that would be a representation of the derivative, wouldn't it? Okay. And again, we don't have an equation for the derivative because we don't have an equation for the function, do we? Okay. So really, the only way for us to estimate what the derivative would be like, okay, is to do this method. Okay. The questions, though, in that problem I want to look at, though, besides actually drawing the graph, and again, I only did it to 3.5. There's more points than that, up to 9.5. You can finish with that. The part A though says, what does the derivative represent? Okay. Well, the derivative here, remember, is essentially a slope. Okay. And if this is measured in feet and this is measured in seconds, then what's the derivative measured in? It's measured in feet per second. Okay. And so that derivative is giving me essentially a velocity, isn't it? Okay. So it's a picture of the velocities at different points in time. Okay. Because again, the y values are feet per second and the time is seconds. So if I said at 3.5, what's the velocity of this particular situation? It would be going 23.3 feet per second. Okay. These are all velocity values here. Okay. All right. Part B says in what units? We already said the units are feet per second. And then it says part C says, can you guess an equation of the derivative by considering its graph? So what they're asking you for here is once you get these points all plotted, and I'm not going to do the whole thing for you because it's one of your homework problems, you can finish it from here. But once you get these points plotted, based on the look of the graph, okay, could you make a guess as to what the equation might be? Or at least what type of equation it would be? Is it linear? Is it exponential? Is it quadratic? Okay. So you're going to make a conjecture as to what you think that might be. Okay. Okay. Questions so far? Okay, one last problem I want to point out here is this number 17. Okay. Looking at this rabbit and fox population. Okay. The questions here, it has ultimately it has the picture of the population curves for the rabbits and the foxes, okay, and it also has the derivative of the rabbit population. Okay, you'll notice that the rabbit population is going up at first, okay, and then becoming a zero slope, and then going down the rest of the way. And you notice that the derivative is positive all the way until it gets here, okay, and then once it gets there, then it becomes negative because again the positive y values of the derivative match up with the positive slopes of the curve. Okay. The negative slopes of the curve match up with the negative y values. Oops, right here, negative y values of the derivative. So looking at the picture, it says what is the value of the derivative? Okay, from figure 310 when the number of rabbits is the largest and the smallest. Okay, so the number of rabbits is the largest right here, isn't it? Remember, this is our population curve. Okay, so what's the value of our derivative there? It's 0. Okay, wouldn't that make sense? For any maximum or minimum, the derivative, it better be what? It better be 0, because the slope of a tangent line at any of those maximum minimum points is going to be 0. How about when the rabbit population is the smallest? It's smallest down here at this endpoint, probably, right? Okay. And what's the derivative like there? Yeah, it's real close to 0 again, isn't it? Because what happens, the population essentially is leveling out, isn't it? Okay. So, which indicates in terms of rabbits, are we gaining or losing rabbits at this point? You know, the population is pretty much steady, isn't it? So its derivative is essentially 0. Okay. How about what's the size of the rabbit population when the derivative is the largest? Okay. Well, the derivative is the largest. Keep in mind we're going from this point up to this point. The derivative is going to be the largest when it's the steepest. Okay. Because if it's steeper, it's going to have a bigger number, right? So if we look at this picture also, okay, we can see that the derivative is the largest here, just like we expected, at 2040. And so how many rabbits are there at that point? It tells us 1,700 right here. Okay. How about when the rabbit population is the smallest? That would be right there. Joe? So it looks like at about 65, let's say. So at 65 up here, it would be right about there. This is where the rabbit population, where the derivative is the smallest. And keep in mind, when we say the smallest, that means the most negative. Okay? So in other words, we're looking for the steepest negative part on the curve. Okay? That's where the derivative is going to be the smallest. Okay? It's going to be largest where it's the steepest in the positive direction. Okay? And smallest when it's steeper in the negative direction. Okay? All right, so what we're at next is we got a little bit of time left to start working on some problems.